Redox processes for electrochemical cells. Essential ideas. Voltaic cells convert chemical energy to electrical energy, and electrolytic cells convert electrical energy to chemical energy. Energy conversions between electrical and chemical energy lie at the core of electrochemical cells. Nature of science. Employing quantitative reasoning. Electropotentials and the standard hydrogen electrode are used in electrochemistry. Collaboration and ethical implications. Scientists have collaborated to work on electrochemical cell technologies and have to consider the environmental and ethical implications of using fuel cells and microbial fuel cells. There's three applications of electrolytic cells. There's electrolysis of molten salts, the extraction of metals or non-metals from compounds in liquid forms. There's electroplating, you can make shiny gold cars. This is just application of a thin layer of usually more expensive metal onto another generally less expensive object. Electrolysis of aqueous salts, this is HL only. The purification of elements or other substances from water or compounds dissolved in water. Well, what's the difference between a voltaic and electrolytic cell? Let's have a look at this wonderful table. For examples, voltaic cells, obviously we have those batteries we looked at in the last presentation. Electrolytic cells, when we refine or extract elements from compounds, when we recharge batteries, we're using electrolytic cells, and obviously the electroplating we just looked at, that gold and shiny car. In voltaic cells, we're converting chemical energy to electrical energy. Conversely, in electrolytic cells, we're converting electrical energy to chemical energy. Voltaic cells are spontaneous, and you can probably guess, since you need a battery to run the things, or you need electricity to run the things, the electrolytic cells are non-spontaneous. You need an external source of energy for it to work. However, both do still have direction of electron flow from the anode to the cathode. Voltaic cells, as we know, form strong reducing agents to strong oxidizing agents, whereas electrolytic cells generally have weak, or not generally, they do have weak reducing agents to weak oxidizing agents. Basic operation of electrolytic cells. We've got a salt here being split up into the metal and non-metal. Bit of a recap. Remember that red cats like to stand next to an ox. This helps us remember that reduction occurs at cathodes and oxidation occurs at anodes. So we have an anode here where oxidation will take place. We've got a cathode over there, which will be the site of reduction. We'll usually use inert electrodes in electrolytic cells, so platinum or graphite. You can see the electrons will be moving from the anode to the cathode. And the anions within the electrolyte are going to be moving to the anode, where they will be oxidized and give up a couple of electrons. The cathode, site of reduction, the cations within the electrolyte will move to the cathode, and that's where they'll be reduced. That's where they'll pick up the electrons that were given over this side. There are different than voltaic cells. First of all, there's a power source. Just a quick reminder from your previous knowledge in science. Perhaps you did it in physics last year, or grade 9 probably. When you look at the cell here, the long line is the positive one, the smaller line is the negative part of the cell. Now this is a big difference. The anode in electrolytic cells is positive, cathode is negative, so they're different than voltaic cells. You just have to remember that. The electrons are forced to flow from the anode to the cathode, from a weak reducing agent to a weak oxidizing agent. It is not spontaneous. You need that battery there. Okay, let's have a look at electrolysis of molten salts. Elements can be purified by the electrolysis of molten binary salts. They need to be molten. That does not mean they're dissolved in water. You've got to get this stuck in your head. We're looking at molten liquids. So you can see here we've got reaction taking place. We're getting a solid, and often it's a binary gas. This is L. It's a liquid. It is not aqueous. It's not dissolved in water. Okay. Another way you could draw it out was of course just as the ions, and if you did, both of them would be liquid, giving you a solid and often a gas given off. The electrodes used are generally inert, so we're using graphite and platinum. And the electrolyte is often a molten salt, such as molten sodium chloride, so liquid table salt, potassium bromide, copper bromide, etc., etc. It's a pure substance in liquid form, and once again, it ain't dissolved in water. It's not AQ. So we've got graphite. If you want to draw this thing out, and you've got the electrolyte is My, and you'd include that little L. Inside of the liquid, you could draw the ions separated out, moving around, free to move, free moving charges. You put in that the anode in this case is positive because it is the oxidation site, anox. Anions in the electrolyte are oxidized. Oops. 1 minute. There we go. And you could draw out that equation showing the anion forming a diatomic gas and giving up some electrons. Here, these electrons will then be pumped by the battery over here to the cathode, which is negative in this case. It's because it's the site of reduction, so the cations are reduced here. Once again, you see that the metal ions are reacting with the electrons to form the metal. Okay, let's have a look at an example of molten salts, the electrolysis of molten salts. We're looking at lead bromide, and you can see once again it is a liquid, and it's going to give us the lead metal and bromine gas. I hear you say, 1 minute, bromine is a liquid, but bromine is produced as a gas instead of a liquid because of the high temperatures needed to keep lead bromide in liquid form. You can have a think about why that is. A hint would be something to do with the IMFs. So what have we got? We've got lead cations, bromine anions, both liquid, giving us solid lead and gas. We're using inert graphite electrodes. Anode is positive because it's where the anions are oxidized, and so the bromine ions are forming bromine gas and giving up electrons, which are pumped around, and you can see here they're getting pumped around the circuit, although they couldn't at the moment because the switch is closed. I'm just going to close the switch. Cathode is negative, it's where cations are reduced. It's where the lead ions get those electrons to form solid lead. Let's have a look at another example. The electrolysis of molten sodium chloride. That's right. Table salt can be a liquid when it's hot enough. So let's get some hot table salt. Remember to write L and make some sodium metal and chlorine gas, which is amazing if you think about it. You've got sodium chloride, which you put on your food, on your chips, and you can make sodium metal, which if you eat it, you would die. It would react with the acid in your stomach and you blow up. And chlorine gas, which if you breathe in, you die. So two things which will kill quite easily when come from a very tasty topping. The anode reaction We've got chlorine ions in liquid form, giving us chlorine gas, giving up a couple of electrons. We've got sodium ion, liquid form, getting those electrons to form the metal. We've got two graphite electrodes, both solid, in our annotated diagram. The electrolyte is liquid sodium chloride. We've got free ions moving around in that liquid, so the charge can move freely. We've got positive anode, and that's where the chlorine ion is going to be attracted to, where oxidation takes place. So it's where the chlorine ion forms chlorine gas and frees up the electron. Electrons get pumped over there with the battery to the cathode, where reduction takes place, and where the sodium ions move towards that electrode, grab an electron and form sodium metal. Let's look at electroplating. Electroplating is an important industrial process. It is used to coat objects with a thin layer of another metal, which often is more expensive. Let's look at this electroplating cell setup. We've got the anode, where oxidation takes place, and the cathode, where reduction is going to take place. The electrons are going to be pumped with the battery from the anode to the cathode. The material which we want to be plated is the cathode, and it will draw in the ions. Here you can see this is what we want to plate on top of this circular cathode. We're going to move over here, we're going to grab the electrons being pumped by the battery, and you get a coating of this metal on top of whatever the cathode is made from. The material that you're going to use to plate metal M, the material which is the source of the plating metal M, is the anode. So this would be M, goes into solution, and then it gets plated over here. The electrolyte is the aqueous ionic compound containing M2+. So this M2+ must be contained within the electrolyte. More of the M2+ comes as at the anode through oxidation, and then it goes over and plates this via reduction. Let's have a look at silver plating, which is great if you like silver spoons, which I do. I will only eat with a silver spoon. We can see the cathode here, where the electrons are being pumped to, is the spoon. So there is a spoon, and it is the cathode. It's going to have a negative charge because electrons are being pumped to it. The reaction type is reduction, and the half equation is the silver ions that are in the solution from silver nitrate, and obviously more silver is coming from here, being reduced to silver metal on the surface of the spoon. The anode is silver solid. It's going to be positive. It's being oxidized as the metal itself is moving into solution and giving up an electron. Oh, and that is the end of that presentation. Splendid.